I hope you can see the document. Okay, participants can now see your application. So last meeting, if you have listened to the video that was already shared to you through Canvas, we were here. We ended on the part wherein we discussed until the second sample problem, talking about the application of the previously derived formulas here on top. That was discussed to those who were present also last meeting. So we are now on this part here on RL circuit uh, problem number 3. Okay, so allow me to read the problem and then go through the solution. So you're given an RL circuit in here which has an EMF of 5 volts, a resistance of 50 ohms, and an inductance of 1 Henry, and no initial current. So you are to find the current in the circuit at any time t. So if whenever you see this phrase, as I have also mentioned last meeting, whenever you see find the current at any time t, it's just asking for the formula. So no specific value for the current because you are to find the current at any time t. Now, if you are to start off with the proper DE, the DE would be di dt plus, so you have Ri equal to the L here. Now, where did that particular, where did this particular differential equation came from? So I would like to clear my drawings and point out for the benefit of those who were not around that if you're given an RL circuit, this is your starting DE. This is the suggested DE that you will start with. It starts with, it has the first term as the derivative of the current. Then you have here the ratio of the resistance and the inductance times the current. And you have here the ratio of the electromotive force E and the inductance. Now, as written, it is really linear because that's the way they always evaluate first order differential equations in terms of its application to circuits or circuit analysis. But whenever possible, you can also do separation of variables, which I have illustrated or given an example last meeting to those who were present. So we will start off with this DE, and that's the reason why you have this now in here, in number 3. So we just substituted the R. Since our L is 1, so it's actually 50 over 1 times I. And you have here electromotive force divided by the inductance, which is also 1, so that's still 5. So as written, actually class, it's linear, but you can solve it using separation of variables. As you could see in here, in the solution that is given, they determined, or the integrating factor was determined first. So I'd like to show to you a simplified way, so hopefully you get to review this again later, on how you're just going to use separation of variables in processing or evaluating your DE. If this is your DE and the right side is just a constant, or more so even if the right side is 0, you can actually solve it using separation of variables without having to resort to having to find the integrating factor and recall the formula for processing linear differential equations. So if you have that DE, so you have di dt here. And I will have a 5 here. I'd like to transfer the 50i on the right side. Then, as you can see, you can factor out the 5. It's common between the two terms. So you'll have 5, 1 minus 10i. As you can see, I have an I here and then I have an I here. So I can separate variables, meaning I'll transfer this one below or under the differential of I, and I can cross multiply the differential of t on the other side. So you have this case now written 1 minus 10i, and you have here on the right side 5 dt. Then you may right away, since we have separated variables, you may right away substitute. So you need to substitute the current initial. So it says there that there is no initial current. So since our variable here is current, so this must be 0 initial. And we're trying to find for the formula for the current at any time t. So you place there in the upper limit I. Now, initial time is always 0 time. And of course, you have here t for the representation of the time. Now, in this side, you can have an expression, or rather you will have an expression in terms of an ln, provided that you will have a negative 10 here and a negative 1 over 10 outside. That's a part of your process of integration. So the left side will yield an expression negative 1 over 10, the ln of 1 minus 10i. Okay? Now, if we will substitute the limit class, you will have actually in the argument of ln a rational expression. One in which you substituted the I in the numerator and one you have substituted the 0 in the denominator. That's after you have already substituted the limits. So if you will substitute the initial current, which is 0, your expression of 1 minus 10i over 1 minus 10 times 0 will be simplified to this. So, amo na siya subong. Ang right side mo, if you will substitute the 0 and t limits, then that would simply be a 5t. Now, if you will simplify, you can transfer the 10 here by cross multiplication, and you have an ln of 1 minus 10i. And you have here negative 50, negative 50t. Now, we will like to make this as the argument of the e. That way, I can eliminate the ln. So that would mean that this one will be the argument of the e and this whole thing here. Simplifying the left side to 1 minus 10i equal to e raised to negative 50t. Now, I wish to have a formula that will solve for the I. So I will transfer this one here to make it positive. I'll transfer this one in here. So that would be 1 minus e raised to negative 50t. And on the right side, I have 10i. So transferring it there will make it positive. Transferring it here will make it negative. Now, I want a formula for the I only, or that's the I of t, the current in your circuit at any time t. So I will divide this entire equation that I have here by 10. If I would do that, I will have this, right? So if I will simplify this one, you will have something like I is equal to 1 over t times. I'd like to write this first because this one is positive. So I have 1 minus e raised to negative 50t. This one, if expanded, is equivalent to the one that you are seeing here. But this one is solved using the process of the linear first order DE, wherein you need to find the integrating factor. What is cumbersome about this process is after you have already determined the expression, you need to substitute conditions. That way, you'll be able to find the specific value of the arbitrary constant of integration C. So, but in separation of variables, you can right away place in the limits when you do your integration. So this is the current at any time t, the one that is asking here. Find the current in the circuit at any time t. So this is the answer that it's looking for. The same answer that we got when we do separation of variables in here. Okay? There is one thing very important for you to take note of in here whenever you're given an RL circuit, okay, an RL circuit, because the expression for your current will have two terms. The one that has the exponential function and the one that is constant. And there are corresponding terms associated, terms that are associated with these terms in your equation. The expression negative 1 over 10 e raised to negative 50 is what we call as the transient current. The transient current. Now, why is it called the transient current? Because this expression dies out or becomes 0 as we substitute infinity to that t variable here. Now, in real processes, in CHE, we call it after a very long time. If we will phrase it in our lingo, after a very long time, that's just equivalent to saying what is t. It's equivalent to saying that t approaches infinity. So after a very long time, what will be the transient response in your circuit, or what is the transient current in your circuit? That would be equivalent to saying 0. Because if you substitute infinity here, the exponential expression will be equivalent to 0. So this entire thing is gone out of the picture. So it's called the transient current because of the fact that as t approaches infinity, this particular term goes to 0 or it dies out. It does not have any value. The other term here is what we call as the steady state current. Now, why we call it the steady state current? It's because standalone, if this is already set to 0, this is the only thing that is left in your expression. So as t approaches infinity, the current I in your circuit approaches the steady state current. So if we say as t approaches infinity, if you substitute infinity in this particular equation, what is left now is 1 over t. And that is your steady state current. Okay? The value of the I in this expression as t approaches infinity approaches this steady state value, which is 1 over 10. Steady state meaning wala na siya nag-change. Nga away siya nag-change because it's a constant. Okay, so take note of those terms. This one is the transient current because it dies out as t approaches infinity. This one is the steady state current because once t approaches infinity here, it's in association with the transient current. This is the only steady state value that remains in your equation. So wala naman kasang may mabilin da ang mabilin ining steady state or constant value of 1 over 10. And as such, it is called the steady state current. So two currents for the RL circuit expression. Once you have derived already the current equation in terms of time or at any time t. Any question? Do you all understand? Okay, so
ang 1 over 10 miss di na sa naghalin miss sa 5 over 50 miss.
ang ano?
Ang 1 over 10 miss.
1 over 10?
Miss.
In here, when you integrate.
Okay.
When you integrate here from your integral calculus, you cannot have an answer that is ln unless the derivative of the u here in the denominator is complete in the numerator. So if you take the derivative of this, that would be negative 10 di, right? Derivative of a constant one is 0. Since you introduce a negative 10 here, to complete the derivative of your denominator, there has to be a negative 1 over 10 before the integral. That way, you did not alter your original expression. Because if you're only going to place your negative 10 di, if you alter the original expression, that is only di. It doesn't have negative 10. So it's as if you did not do anything to change your original integral. You actually multiplied the original integral by negative 10 over 10. So ang negative 10 lang ang gimbutang mo dire, pero ang negative 1 over 10 bilhin di sa sagwa. If you multiply these two, that's just but 1. So that is where your 1 over 10 came from. This is when you do separation of variables. But if you don't do separation of variables, you do evaluation of this DE using the technique for linear first order differential equations. Then I think I suggest you need to review on our topic on how to evaluate first order DE because we're done with it already. You can see there on where 1 over 10 came from.
Okay, miss. Thank you.
Sige. Question? Some more question? Okay, I will erase here so we can scroll down to the last sample problem in this page. This time, so the first three problems here concerns an RL circuit. So we started with a source-free RL circuit. Wala siya sang source. Then actually number 2 is a specific problem associated to number 1. It's a source-free RL circuit also. You have the inductance and the resistance here. Okay, the inductor and the resistor. And then this one is not anymore source-free. Sample problem number 3 is not source-free because you already have this EMF. Okay, It's source free when you don't have a electromotive force. Okay, no power source. Now we go to number 4. This time we go to an RC circuit. So in RE circuit, which is not source free in this case because it has an EMF. This time, as I have mentioned to those who were present last meeting, your EMF is not constant. Here in sample problem number 3, the EMF is constant at 5. This one is a function of the cosine function. It could even be a function of the sine function. So in this case, your RC circuit is an AC circuit because the EMF changes with time. It's a function of time. If your EMF is constant, it's a DC circuit. Source is battery. Okay, so for this RC circuit, the resistance is 100 ohms and the capacitance is 0.02 farad, or that's 0.01 rather. That's equivalent to 10 raised to negative 2 farad. Initially, there is no charge in the capacitor. So it's like saying, so let me go up. It's like saying that Q is equal to 0 at time equal to 0. Or you may write it as small letter q because the way we represent the charge is small q. Now, in this problem, you are to find the current at any time t. So it's still an expression for the current at any time t, or a formula that will solve for the current at any time t in your circuit. Okay, now what you have here on the next statement is already an explanation of what's being done in here. So the next question would be, how will you start solving the required here, or how do you start finding the required information since you're given an RC circuit? So what you're going to do, you go back to the fundamental DE for an RC circuit, which I've shared last meeting, and this is that particular differential equation. The rate of charge in the capacitor plus the charge divided by the product of the resistance and the capacitance should be equal to the electromotive force divided by the resistance. And by the way, this model DEs for the RL and RC circuits are based on Kirchhoff's voltage law, wherein the sum of the voltage drop across your circuit will always be at all time equal to 0. So that's the basis. So this is our model differential equation for an RC circuit. Associated with this model is the fact that the current passing through your capacitor is actually the rate of change of the charge of that capacitor with respect to time. Now, current is the rate of change of the charge in the capacitor with respect to time, or it's the derivative of the charge with respect to time. So these two equations, the differential equation and this other differential equation, goes hand in hand whenever you try to determine required information related to an RC circuit. Okay? So now we will use, so you have this in mind already, we go back to that problem of ours and use that DE. So we started with that DE. Okay, we substituted the EMF, which is 400. Actually, it's 400 cosine 2t. However, in the formula, it's EMF over R, or it's E over R. Our R is 100 ohms. So, amo na nga nag 400 na lang ni kay 400 divided by 100, that would be a 4. Now, this Q is supposed to be divided by the product of R and C. So, your R is 100 ohms, your C is 0.01 farad. So, if you multiply these two, that will simply be equal to 1. So, that is why you don't see any other number here multiplied to Q except 1. Because the product of this 100 and 0.01 is 1. Then we have the charge here, the derivative specifically of the charge with respect to time. This equation, class, cannot be solved using separation of variables anymore. Why? Because we cannot separate variables. This is really to be solved using the linear DE approach. And how do we solve a linear DE? How do we start solving a linear differential equation? Anybody who would like to suggest how do we start solving a linear differential equation? Okay, find the integrating factor. Thank you, John. Find the integrating factor. Now, class, you have seen your grades already, and I think you have seen that you made it, even though probably you were surprised that you made it. It's because your classworks were all complied with. So classworks is 20% of the grade. But if you're really going to look into your quizzes, it's really very dismal because it really tells me that you do not know how to evaluate. For some, you don't know how to evaluate. For some, they do. So do something about it. It's just we tweak the grading system. Actually, it was not tweak because that was really the existing system in the online setting, because we understand the challenge that you are facing, especially with online learning. Now, when I ask a question and if only one or two will just answer me, it just tells me all the more that you even forgot how to process it. Now take note that you're not yet saying goodbye to the techniques that you have learned in the past because you're applying it now. So if you have forgotten it, please do your homework, do your what you think is the most responsible thing to do. You go back to the lesson that we have discussed in the past and know how it's going to be applied to what we're talking here. And not just simply that, especially junior exam or in some quizzes, that if you're given a multiple choice problem, you just simply leave it to chance that ang base magtsakto akong palagpat kisa sobra pa man sa palagpat, sobra pa ang palagpat sa tsakto, then don't do it, because later on you will be, of course, using critical thinking in a much higher level when you go to your professional subjects and when you prepare for your board exam. Okay, so when we determine, going back to this one, thank you for that, John. When you determine the integrating factor, excuse me, class, ha? If you will determine here the integrating factor, so that would be based on the P of t here, or the P of x as we were discussing linear then. So your P of t is just one, so that would be e raised to the integral of dt. And as such, your integrating factor in this sense is e raised to t. Okay? Now, since it's e raised to t, if you recall the process of processing a first order linear differential equation, the left side of that formula, which I simplified for you, would be the unknown function. In your case, the unknown function is q, multiplied to the integrating factor e raised to t. And the right side would constitute of the integral of the product of q of t. And this is your q of t. So you copy the entire expression and you multiply it with the integrating factor. And you place your dt. Now this side, you don't have any problem because you just have a case of multiplication. In this side, you will use integration by parts. So then we go back again to the challenge of having to know how to evaluate an integral expression using integration by parts. So you may have u here equal to e raised to t, and you may have the dv equal to cosine of 2t dt. Or if you wish, you may have the other way around. You can have the u as the cosine of 2t and the dv as e raised to t dt. You will still arrive at the same answer. Now, if this is your u, your du is e raised to t dt. And your v in this case, since this is a cosine, is 1/2 the sine of 2t. Okay, if you want to know whether what you have done here is correct, is you just differentiate this and it will give you this one. Okay, so this is sine 2t times 1/2 times 2. So that would be giving you a derivative which is cosine 2t dt. Now, how is the answer here to be interpreted? So we keep what is on the right side. So we have 4 times. So we cross multiply. So this is 1/2 e raised to t, the sine of 2t. And minus what? The integral of 1/2. So it's uv minus v du. So this one, you have integral of e raised to t, the sine of 2t dt. So you see here in the process that you're not done with the by parts integration one for the first time, because you're going to integrate again this one. So I will write here for integral of cosine 2t e raised to t dt. Okay, we will just keep that one here because my answer, the answer that I have written here is actually for this one. So that we will know what's the answer for the integral of cosine of 2t e raised to t dt. So you will do another by parts here. So you will have another u, which is e raised to t, and a du, which is e raised to t dt. Then you'll have here a dv, which is sine of 2t dt. And you have a v, which is negative 1/2 cosine of 2t. Okay? I'm sure in your integral, there's a shortcut formula for such expressions as this. And what I'm doing here is the fundamental basic principles of integration by parts. So if you wish to go back to that shortcut formula in processing expression of cosine theta, e theta, d theta, it's okay with me. Okay, as long as, of course, you understand where that particular formula came from. I'm just doing it in here because I'm not the type who will go back to shortcut formulas when I am discussing, because I want to show how it's done, the basics that is. So now you have canceled this one here. So I will just have this one, 1/2 e raised to t sine of 2t. Okay. Now this one, this negative 1/2 will be multiplied to this one. So you have negative 1/2 e raised to t cosine of 2t minus, that's still the integral of this, uv minus v du. So this is negative, so make this positive, because minus the integral of v du. This is negative. So you have now, I'll place it here, 1/2 cosine of 2t e raised to t dt. Now this expression, the three expressions I have written here, is actually equal to the integral of cosine of 2t e raised to t dt, class. Now, if you will simplify this, I like to write it here because I cannot scroll down. You will not see that anymore. So if you will simplify what you have there, and this 1/2 of cosine 2t e raised to t dt will be multiplied to this 1/2 here. You see this? Because this 1/2 should be distributed to this 2. That would be now negative 1/4 integral of cosine 2t e raised to t dt. Now, since this is a cosine of 2t e raised to t dt, it's the same as this. You can place it here on the left side. So that's the time in your integral then that when you do by parts here, the expression, if the expression in this side is similar on the left side, you transfer it here on the other side and find the integral, the resulting integral then. So remember, I have already negative 1/4 here. So if I transfer it to the right, that would be positive 1/4. Plus 1/4, and this one, that would be 5/4. So I will place here 5/4 integral of cosine 2t e raised to t dt. I hope this makes sense. So this is 1 and this is 1/4. So 4/4 and 1/4, that would be 5/4. So that's on the left side. On your right side, what you have is this. You just copy 1/2 e raised to t sine of 2t, and this one we have already transferred on the left side. So that's positive 1/4. So plus 1/4 e raised to t cosine of 2t. Okay, since you have 5/4 here and you intend to know the cosine of 2t e raised to t integral, you multiply this entire equation by the reciprocal of that, and that would be 4 over 5. So what will happen? The cosine 2t e raised to t dt integral that is written here will be now replaced by whatever expression I will have in here. Okay, so kopyahon ko na siya ha. So I will place here q times e raised to t is equal to, remember, we have now the integral of cosine 2t e raised to t dt in here. I will just multiply the equation by 4 over 5, so I will get rid of this. The constant 4 is still in here, so I'll place 4 and I will multiply by my answer in here. So if I will multiply 1/2 here by 4 over 5, my answer will be 2 over 5. 2 over 5. And you notice that I have a common factor that is exponential. So I will place here e raised to t. And this one is 2/5. And this would be sine of 2t. For this one, that would be plus 1/5. Okay? Makancel na siya ang 4 cosine of 2t. So your answer would be the one that you are seeing here. So you have q times e raised to t is equal to, this is common. I'd like to distribute the 4 in here so you'll see the exact thing. So I will have e raised to t multiplied to 8 over 5 sine of 2t plus 4 over 5 cosine of 2t. Remember that this is an integral. There has to be an arbitrary constant of integration. So I'd like to write it here so you will see plus the c. Okay? Now, since you have only here the q, meaning this e raised to t here was transferred to the left side, or the right side rather, by division. So what will happen? You'll have q equal to, this cancels out and leaves you with 8 over 5 sine of 2t plus 4 over 5 cosine of 2t plus c e raised to negative t. This is that thing that you are seeing here. But look, whenever you see like solutions manual or resources in the internet, they don't give you the process like this. They will simply give you something like this. And it only tells the person who is reading your work that how did it become like this? So you have to show all of this, and that's where the challenge is, because kung di ilang yaan mo lang man yung DE niya. Pero ang pag-process ng integral, that way you evaluate your differential equation is where the challenge really is. Now, this is already class. This is already your Q. Your Q expression. Now, but the problem is not asking for the Q. It's asking for the current in the circuit at any time t. So where do we get the answer to that? So you see the statement that I have placed here. To solve for the I, differentiate the Q equation and substitute for the time in seconds. Why will you differentiate the Q with respect to t in this case? Why will you do that? Now, I will erase everything that I've written here except this equation. Anyway, we have already seen that. So I can use the vacant portion. That our equation, the equation that we have out of processing the linear DE is the same as the one that you see here in the solution. Okay, so we'll erase everything so I can use the vacant part. So that's our expression there. It's difficult to keep on transferring on the board, the Jamboard, because I will keep on transferring page at times. It lags. Okay, so in here, class, you can see that you still have the C, and this is not yet the answer that the problem is looking for. So what will you do? You first find the C. How do you find the C? You use the initial conditions that is given in the problem. Now, what did it say about the charge? Initially, there is no charge on the capacitor. I wrote it here a while ago. This Q is 0 at time equal to 0. So to determine the value of the C, you substitute that condition. So you have the 0 equal to 8 over 5, the sign of 0. Substitute 0 here, plus 4 over 5. That's plus. Cosine of 0 plus C e raised to 0. This one is a 0, but the cosine of 0 is 1. So you'll have a 0 equal to 4 over 5 plus C. That tells you that C is actually negative 4/5. See this one here? That's because you have substituted that Q in the statement here, the Q being equal to 0 at time equal to 0, because there was no charge initially in your capacitor. Now you can replace this C with now the value negative 4 over 5. This should be negative. Okay, Arisha, negative 4 over 5 e raised to negative t, that one. And you have 8 over 5 for the coefficient of the sine 2t. And you have 4 over 5 for the coefficient of the cosine 2t. This is your Q now. So you may wonder why will we differentiate the Q expression, Miss Ali, with respect to time? Okay, anybody who knows the reason why we need to differentiate the formula, the expression of the charge in your capacitor at any time t with respect to time? Okay, somebody wrote in the chat box, Christian, because current is equal to dq dt. Very good, Christian. So that's it. Where is it taken, Miss? Some may be wondering why di na siya nimuging kwa, Miss. It's in here. So I will clear all the markings. Anyway, you've seen already what you need to see here on top. I've shown it to you when we start before discussing that for the current passing through your capacitor, it's a derivative, or it's the derivative of the charge in that capacitor with respect to time. So that's the purpose of that expression. So meaning, if you intend to finish this problem here, it was just explained in here, how will you find the current? So you just differentiate. You just differentiate this one. So your current is equal to dq dt, and it's equal to the derivative of this. So anong derivative? Sina? So you have so that would be now positive 4 over 5 e raised to negative t, because this negative 1 will be multiplied to this. And then you have, for the sine, it's cosine, but you have the 2. So this would be 16 over 5 cosine of 2t. For the derivative of the cosine, that's negative sine. So I will have negative 8 over 5 sine of 2t. So given the time in seconds class, you will be able to determine the current passing through your RC circuit. Not source-free, but a complete RC circuit in which your electromotive force is a function of time. Do you get it? So your answer actually to this problem is this equation. Any question? No question? So the real challenge here, class, is this. You have to recall your calculus again, processing of the integral using integration by parts, and you pair that with the newly given concept of the application of Kirchhoff's voltage law in writing down the model differential equation. And this is it. This is your model differential equation only applicable to this case. So if we change the circuit, the model DE changes. However, I have emphasized also last meeting that we will just limit our differential equations here to the two types. Okay, what are the two types that I need? We need only to limit to, that would be these two circuits only. Because If we'll have all three elements present in our circuit, meaning we have the resistor, the capacitor, and the inductor, your circuit will not be a first order DE. It will be a higher order DE, and that will be something that we'll be discussing next week. Okay? Any question here? Okay. If there aren't any question here, I will go to a different document. So I will share again. Then just let me know if you can see. I gave you 4 additional documents there. They are all containing sample problems. Since we have time, I'll go through the RC circuit, source-free RC circuit. Let me know if you can see the document. Can you see the document?
Yes, miss.
Sige, sige. So anyway, I just transferred to a different tab. So this is for your RC circuit. The 4th sample problem I gave you is a complete RC circuit, but this is just but a review because this one is also shown there in the original file, the RLRC series circuit application file. So this particular document starts with everything that you need to know regarding the capacitor, the current on it being equal to the derivative of the charge with respect to time, and that the charge in the capacitor, if determined using a non-derivative expression, is actually the product of its capacitance and its voltage. Okay, so CV. So the charge in coulombs, the capacitance in farad, and of course voltage in volts. Now, if you will multiply, or rather if you will substitute, not multiply, this CV expression to the Q that you have in here, you will have a different expression, class, another way of determining the current that is passing through your capacitor. And this expression now is not dependent on the charge. It's now dependent on the rate of change of the voltage across your capacitor over time. So, paano nag-change ang voltage sa capacitor over time? Multiplied by the capacitance. Now, wonder di na siya mis naghalin. This Q is replaced by CV here. And since capacitance is fixed, it's a constant, only voltage is changing. So when you differentiate, you just set aside the constant C, and you have here the derivative of the voltage with respect to time. Or this is the rate of change of the voltage with respect to time. As such, this expression has now the set of units voltage over second. Now, this was discussed in the previous meeting. So, if current is 0, the capacitor is acting like an open circuit, and this is when voltage is constant. So, meaning, initial constant. So, if this is constant, derivative of a constant is 0. It follows that your current passing through your capacitor is 0, meaning it's acting like an open circuit. Wala may nag-aagi na current. You have already a sample problem on the source-free RL circuit last meeting. Now, this is the source-free RC circuit. No voltage here, no EMF. So, when you sum up the current leaving this particular node, it's also equal to 0. So, if we have this nodal analysis applied to this node here, the total current leaving it must be equal to 0. So what are the currents leaving this node here? So that would be the current through your capacitor and the current through your resistor. So we add the two. Now take note that you will go back to what you have in here regarding the current expression. So if you will replace the IC, the current through the capacitor, by this expression class, the C dVdt. So you place it in here. And this one was taken from the formula of the voltage drop across the resistor. So V across the resistor is equal to the product of IR. So if we get an expression there for the current, that would be V over R, and it's equal to 0. If you simplify this DE, we divide the entire expression by C, this will be the resulting expression. Okay, it is written here that this is first order linear. I'm sure you know why it's first order linear, but this is also separable. Okay? This is also separable. So let me just show to you how this one came about. Okay, it's almost time. So since it's separable, though there is nothing wrong with the statement here that this is first order and linear, but this is easier tackled using separation of variables. So you have dv over dt, transfer that one here, v over rc, then transfer this one here in here. So dv over v is equal to 1 over rc dt. Then integrate. Initial voltage in your capacitor, voltage at any time. Initial time is 0 and you have your time t. I'll get an ln of v over v sub o, and that would be 1 over rc times t, because this is anyhow t minus 0. We make the left side and the right side of our equation, again, the argument of the e to simplify the left side. So I will have v over vo equal to 1 over rc times t. But I missed something. Okay, what did I miss? The exponential function. So this would be, this would be e raised to t over rc. It follows that the voltage at any time in your capacitor is equal to its initial voltage times e raised to t over rc. This is the formula that you are getting here. This k is the arbitrary constant of integration. Once the limits are properly supplied, it's anyway discussed in here, at time equal to 0, voltage is v sub o, you will have this formula. A new formula to memorize or to take note of concerning a source-free RC circuit this time. Source-free meaning wala ta EMF. Now, if this formula is compared parallel to this one, this is the formula for the current across your inductor in an RL circuit. So you have this as the transient current, or the transient, specifically, generally, the transient response to your source-free RL circuit. It was discussed last meeting. So this is your formula. It allows you to solve for the current in your circuit at any time t. Specifically, it was shown that I is equal to IO e raised to negative R over L times time. This is for an RL circuit. You see here an inductance. This is for an RC circuit. You see here a capacitance. Okay. Now, when is this formula used? When you are given a source-free RC circuit. So now you have another formula to add to a formula that is pre-derived regarding the RC circuit. Source-free, that is. Okay? Let me clear my markings. Now below, you have the behavior of the voltage as time increases for an RC, a source-free RC circuit. This is exponential decay, exponential decrease in the value of the voltage as time increases. Okay? Now, if you want to change the formula, not change, but look for an alternative formula for the charge in your capacitor, wherein you will be using this formula here for the voltage. Is so easy. Islan mo malang ni ang V sang sininga pre-derived. So you have now an alternative formula for the Q, the charge in your capacitor, taken from the fundamental basic formula that it's equal to the product of C and V. So now you have here the charge for the capacitor, source-free, in a source-free circuit, in terms of its initial charge and the time. Of course, you have to know the resistance and the capacitance. Okay? The highlighted formulas that I have placed in here are formulas that are only applicable to the case that is given. Kung ano na siyang case na ginadiscuss, dara na siya applicable. Once it's not source-free class, you have to set up a new DE. How will I set up, Miss, a new DE? You go back to this one. Okay? So kung hindi na siya source-free, and you are given an electromotive force, I suggest that you go back or you use the technique that we have discussed in sample problem number 4 a while ago. Okay? Now, under this one, I think I place another formula for the current passing through your capacitor. But this time, this is only for a source-free circuit. Again, going back to our example number 4, a while ago, we have a current that has 3 terms. Tatlo to ka-term because that particular circuit is not source-free. This one is source-free. So this is the current for a source-free circuit in terms of the voltage, the resistance, and the capacitance. Okay? Now you have here the current as well. If we change the Q expression that we have in here in the derivative to the Q expression in here. So gina-islan-islan lang. My suggestion is you should know the basic DE. You should know the relationships of the current to charge and the charge to capacitance and voltage. Or para hapos nga hindi na ikaw mag-derive, you write down a summary of formulas. So sulat ka ng summary of formulas for a particular case. So for a source-free circuit, RC circuit, amunin ako mga formulas. Kung hindi siya source-free, ma-started ko sa DE, kag ma-differentiate ako kung ano ang need ko sa current. And that's it. Okay? The other documents that were shared to you, just let me borrow a few minutes. This one, these are all sample problems. You can read on this, but please don't anymore bother to study the part which has the impedance, the Z. Okay, si Miss Francisco maybe Miss Francisco or whoever will teach you circuits later on. May aray ko di sample problem sa punta nga ginhatag ko sa duha files nga may Z na siya. So if it has the Z already, don't study that anymore. That's for you. Maybe you can use it later on. But it's not anymore included to us. What you just need here in RC application, important, very important, are the 2 model DEs for the RC and the RL circuits and the relationships between voltage, current, in the case of the RL circuit, and the relationship between voltage, charge, and current in an RC circuit. Okay, sa RC, may bago kita nga gina-consider nga electrical quantity, and that is the charge. Lain niya sa RL nga masakpos lang, kinalanta lang yung current voltage. Pero sa sa RC, may charge pa kita nga, take note. So when you study, write down the set of formulas that you need because that will come in handy later on when you solve a problem, especially if the case that is given you is exactly the same, only with the quantities changing or different later on. Okay? Okay, I will stop sharing now.